We're going to start using ratios and proportions to help us with similar polygons. So first off, let's talk about what similar polygons are. So in similar polygons, all angles are congruent and all sides are proportional. So it means it's the same shape, but it's a different size. So congruent polygons mean that all angles and all sides are congruent, but in similar polygons, all the angles stay congruent, but the sides are proportional. So let's look at these two. So we can tell by the drawing, since they have the two right angles, they're perpendicular to the two sides, so that would make those sides parallel. These are trapezoids. So trapezoid ABCD is similar. We use that one little squiggle to show similar. ABCD is similar to PQRS. List congruent angles and write the ratios of the sides in a statement of proportionality. So if we start with our angles, remember that the way that they're named can be very helpful to us. So list congruent angles. If we start with angle A will be congruent to angle, so since A comes first, angle P. So this lower left to lower left. So angle A to angle P. The next one will be angle B, and so that one comes second. Angle B is congruent to angle Q. Angle C will be congruent to angle R, and angle D will be congruent to angle S. So there are all of the angles in their congruent part. So the next thing is to write the ratio of the sides in a statement of proportionality. So if I want to say AB, AB, and we're going to put its corresponding side as part of its ratio. So AB will be proportional to PQ. And that's our first ratio. So let's move on to BC. If I'm looking at side BC, it will be proportional to QR. If I use CD, CD will be proportional to RS. And finally, DA or AD will be proportional to PS. So we can also use the way that they're named to help us with those sides. So in similar triangles, sides aren't congruent, but they are proportional. So now we can use these to help us solve problems. So we can figure out, are these triangles, or are these figures similar? They both happen to be sets of triangles. So if they're similar, then all of our angles will be congruent and all of our sides will be proportional. So here I have a 60-degree angle that's marked and it's congruent to this one, so this angle will also be 60 degrees. And let's first test and see if all the angles are congruent. So we have a 60-degree angle and an 85-degree angle in the same triangle. So I can figure out my last angle here by adding these together. So 60 plus 85 is 145. And I can take that away from 180. So 180 minus 145 will be 35 degrees. So since this angle is 35 degrees and this angle is 25 degrees, that would make this angle 60 plus 25 is 85. So 180 minus 85 will give me 95. So we do not have all angles congruent. So these are not similar because not all angles are congruent. So if we can prove that not all the angles are congruent, then we don't even have to worry about the sides being proportional. So in the next figure, we have some markings. So this angle is congruent to this angle, and we have a second set of congruent angles. So if we know that these are the same, then since we have two sets of congruent angles, we know that the third angle will also be the same, just because they have that angle sum of 180 degrees. So we need to check our proportional. So let's look at this side first between the first angle that's marked and the second angle. So in the big triangle, that's 18. In the small triangle, that is 6. So we have a ratio here of 18 to 6, or we could reduce it to 3 to 1. Let's see if it's equal to our next one. So now we can use the side that is attached to the angle that's marked number 1. So in the big triangle, that is 9. In its corresponding side, the one that's marked with the 1 angle, is 3. So far, 9 over 3 also reduces to 3 to 1. So that one's good. Let's check our last set of sides. So our last set of sides will be 12 in the big triangle. And in the small triangle, it is 4. And 12 over 4 also reduces to 3 to 1. So all of these have a ratio of 3 to 1. So 3 to 1 makes it similar. So these are similar triangles. So in our next example, we're told about a relationship that is similar. So a painting is similar to the wall on which it hangs. So here we have a painting of a flower. We want to calculate the scale factor, and the scale factor means what it's being multiplied by. So like in the other one, our scale factor was 3 to 1. Our bigger triangle was 3 times as large as the smaller one. We're going to calculate the scale factor and find the ratios of the perimeters and areas. So we kind of have a loaded problem here. So first, let's check our scale factor. So our scale factor is going to be the ratios. And we can use either one. Sometimes it'll tell us which one to use. For this one, let's start with the small one. So the small one has a ratio of 6 feet to the large one is 15. So we can use 6 over 15. And that will reduce to 2/5 whenever I divide by 3. And I could also use 3.2 to 8. And whenever I work out getting this decimal out of that first one, I would also get 2/5. So the ratio, if it tells me they are similar, then the ratio of one side will work. So this ratio is the scale factor. All right, the next thing we need to figure out is the perimeter. So let's find the perimeter of the wall. And to do that, we're going to do 15 plus 15, which is 30, plus 8 plus 8, and that's 16. So 30 plus 16 gives me 46 feet. Then I can find the perimeter of the painting. And so I have 6 plus 6, which is 12. And then 3.2 plus 3.2 is 6.4. So 12 plus 6.4 is 18.4. So if I want to find the ratio here, I need to keep with my same thing. So this is painting to wall. So to find my ratio of my perimeters, so the perimeter of the painting was 18.4, and my perimeter of the wall, we're running over my 8 over here, so let me put it over here. The perimeter of the wall was 46. So I want to divide this out, and I'm going to divide it out, and I get 18.4 divided by 46, which is 0.4. And we know that 0.4 is 2/5. So this is the ratio of the perimeters. So notice that our scale factor and our ratio of our perimeters ends up the same. Let's see if we can figure out a relationship with the areas. So next we have to do the area of each one. So let's start with the smaller one this time. The area of the painting is going to be length times width. So 6 times 3.2 gives me 19.2. And the area of the wall is going to be 15 times 8. And that will give me 120. So here, the area of the painting over the area of the wall, just keeping with the same ratio that I started with the beginning, I'll have 19.2 over 120. And if I divide that out, 19.2 divided by 120 is 0.16. So 0.16 is going to be, so that would be 16 over 100. Divide both of those by 4, and we would get 4/25. All right. So let's come up with a connection. So we'll say scale factor, ratio of perimeters, and ratio of areas. I want to use lowercase r's though. All right, so what we found right here in between these two is that our scale factor is the same as the ratio of our perimeters. So scale factor equals the ratio of the perimeters. Notice that these are each lengths. So lengths, they're just the area or the length around. So since those are just lengths, they stay the same. If you find the scale factor, you also have the ratio of the perimeters. So now what's going on to get me from 2/5 to 4/25? So if I have 2/5 and I need to do something to it to get to 4/25, notice that 4 is 2 times 2, and 25 is 5 times 5. So what we have here is we have 2/5 squared that gives us 4/25. So our relationship here is that scale factor squared is my ratio of the area. And that's because I'm not just looking at the length around it, now I'm actually filling it in. So the ratio has 2 dimensions, that's why I square it. The areas have 2 dimensions. And that goes for any problem that you work like that. All right, finally we have parallelogram ABCD is similar to parallelogram GBEF. And we have some links listed for us. We can also use the names to help us set up some ratios. So what I have is I have EF and GF given to me, and I have AP, or AD, sorry, and I need to find CD. So I can set up my ratios either way as long as I keep things lined up. So maybe I'll choose to go small parallelogram to large parallelogram. So if I go small to large, then I'm going to have to keep like my height here and my length down here separate. So from small to large, let's use the ones that we know together. So GF, if I start with GF in the small, so that's G and F, then in the big one, that's going to be A and D. So just to double check to make sure that they're lined up, we can use those names. And for our other sides, we can use, so starting with this EF, and if I use EF, those are the last two, that would be CD. So first I'm just going to double check and make sure that everything's lined up like it should be. These are both in the small parallelogram. These are both in the large parallelogram. And we double checked with the names and made sure that those actually line up. So the length of GF is 15. And the length of AD is 24. So that's going to help me with my scale factor. So for the other one, whenever I set it up, EF had a length of 12 and CD had a length of y, and we need to find y. So it's over here, it got covered up a little bit. All right, so notice that if we would have set it up another way, our cross products would have stayed the same. So we're going to do our cross products. We have 15 times y. That is 15y. And then we have 12 times 24. So 12 times 24 is 288. So to find y, I'm going to divide by 15. And 288 divided by 15 is 19.2. All right, so now let's just double check and see, make sure that it makes sense in terms of the problem. So 15, the bottom side was 15, the diagonal side over here was 12. So 15 was bigger than 12, 24 is bigger than 19.2. So it fits within the context of our problem. So we have our answer for y. So we can use these similar triangles and the relationship between their sides to solve for missing parts.